Hello and welcome. So we'll be solving another interesting question on bending stresses in a beam. It says a steel plate of width 120 mm. Our width is also known as what? Base, which is B. Alright. And thickness 20 mm is bent into a circular arc of radius 10 meter. Right, and we are told to determine the maximum stress induced and the bending moment which will produce the maximum stress. So we said we are told to take E to be equals to 2 times 10 to the power of 5. So we'll be starting with the given data. All right, so the given data here, we have the base, which is also known as the width. B is equals to 120 mm. All right, and we are given the thickness T, which is equals to 20 mm. All right, and we are given radius to be 10 meter, which is going to be equals to 10 times 10 to the power of 3 mm. All right, and we are told to take E. So we want to find our maximum stress, and want to find the maximum stress and then the maximum bending moment. All right, and then we are told to take E as 2 times 10 to the power of 5 Newton per millimeter square, which is our Young modulus. All right, so for us to solve this question, of course, here they are dealing with thickness and what, and base, that is thickness and width. All right, so this T is nothing but it is just like a rectangular in nature. You understand? So we'll be treating this as a rectangle. You understand? But we'll be replacing the depth in a rectangle with what? With thickness. So we are going to be taking the properties of a rectangle for this question. And for us to start with, the first thing we are going to calculate here is our moment of inertia. All right, so what is the moment of inertia? The moment of inertia, I, is equals to what? BD. Instead of us to write D here, is going to be what? T. I hope you understand. That is thickness. That is thickness to the power of 3 divided by what? Divided by 12. All right, for a rectangle. All right, so we are going to substitute now. Substitute here, we are going to have our base to be what? 120. So we are going to have 120 multiplied by thickness. What is thickness? Thickness is 20 to the power of 3 divided by 12. So if you press this value where, you are going to have this to be nothing but what? 8 times 10 to the power of 4. 8 times 10 to the power of 4 mm to the power of 4 as well. All right, so now the next thing we are going to be doing here is this. You are going to recall carefully from the Flexural equation. And the Flexural equation, we know it is what? M all over I, which is equals to E all over R, which is equals to stress all over what? Y. All right, so here we know that we know what we don't know the value of our maximum bending moment. We don't know, okay, we know our I. All right, and the first thing we want to calculate here is the maximum stress, right? So don't forget, we are given radius, right? We are given radius, that is the radius of curvature. So we know our radius of curvature, we know our what? Our modulus. And we want to find our stress. We haven't solved the value of our Y. And for a rectangular section, our y value, that is the distance from the neutral axis to the outermost part of that section, there is going to be what? D divided by 2. So here is going to be thickness divided by 2. So here our y is going to be equals to thickness divided by 2. So which is equals to, our thickness is 20. So if you divide that by 2, you are going to have 10 mm. Alright. So now we are going to be equating this formula for this now. So we are going to have E all over R will be equals to stress, that is the maximum stress, all over what? Y. And if we make our maximum stress the subject, so we are going to have this to be E multiplied by Y divided by what? Our radius. Alright. So if we do this, we are going to have our maximum stress to be equals to our Young modulus, which is 2 times 10 to the power of 5, then times y. Our y is 10 as well, then divided by our radius. Our radius is 10 times 10 to the power of 3. 10 times 10 to the power of 3. Alright, so this 10 here will go with this 10 here, and 5 minus 3 is 2. So our answer is going to be 2 times 10 to the power of 2, which is 200. So our answer here is going to be 200 Newton per millimeter square. Alright, so that is going to be our answer for the first solution. Alright, so for the second solution, which is the maximum bending moment. So here we are asked to find the maximum bending moment. So which is this? Now that we know our I, we know our Young modulus, and we know our radius, so we are going to be equating this equation for this. So we are going to say that our M is maximum bending moment all over I will be equals to E all over what? R. So if you make our maximum bending moment the subject, so this will be equals to E I all over what? All over R. So let's substitute there. So we are going to have maximum bending moment to be equals to our Young modulus. Our Young modulus is equals to what? 2 times 10 to the power of 5, then times I, that is the moment of inertia, which is 8 times 10 to the power of 4, divided by our radius. Our radius is 10 times 10 to the power of 3. 10 times 10 to the power of 3. Alright. So this 10 times 10 to the power of 3 is 10 to the power of 4, which we cancel out this. 2 times 8 is 16. So the answer here is going to be 1 point, that is 16 times, let me write it, 16 times 10 to the power of 5, right? Yeah, 5. Alright. So because it is a maximum bending moment, it's going to be Newton millimeter. So furthermore, you can take this value to be in meter. Alright, so for us to do that, the answer here is going to be 1.6 kilonewton meter. 1.6 kilonewton meter. Alright, but if you don't want to convert it to be in kilonewton meter, you can just leave your answer like this. Alright, so here hence the solution to this question. I believe we understand this. Thanks.